think it is about time to start our Knowskite X webinar on machine learning and hybrid modeling for materials discovery. I'm very happy to welcome you all here on behalf of the Knowskite Consortium. This also gives me the time to thank very much our organizers at Warrant Hub who helped us announce this webinar and set everything up. So this is very much appreciated. Thank you so much for your help and your work in this. And I'm quite sure that this will be a huge success. So just very briefly, welcoming is already over. So I can now sit back and relax and hear your interesting talks, which will start with an introduction by Professor Elise Berrier, the project coordinator. She will give an introduction to this to the project. And then we will start with technical presentations by Dr. Jürgen Spitaler, by Professor Andreas Hauser, Sean Cody, and Professor Robert Behartz. In the middle, we will have a short coffee break. And at the end, we will have a roundtable discussion where I hope that all of us participants will stay and be able to reflect on what we have heard in the 4 technical talks and its connection to the Knowskite X project. Yes, without much further ado, I would like to hand over the word to Elise. And if you could tell us a few words about the Knowskite X project so that our guests are informed about the project that we are working on, that would be much appreciated. Thank you very much, Elise.
Thank you, Bernard. Thank you very much. I don't know if you see my screen. Is it
yes, we can.
Yes.
Okay, they're very fine. Okay, so just a few words on the context of this webinar. It's about the Knowskite X project, and just let me share an overview with you. So this is a picture showing the Knowskite X people. It was at the beginning of the project during the kickoff meeting. Now, as the group has grown up by now, we are gathering people from several countries, Italy, among which Italy, Austria, France, Spain, Greece, and also Portugal. And let's come now to the basic concept. The idea is to discover and optimize new functional materials for energy conversion and storage. And in particular, we've been quite interested in developing perovskite-based materials. So this is the basic structure of a perovskite. You have a A site cation, a B site cation, and X. In our case, X will be oxygen. Who can be A or B site cations? Almost every single element of the periodic table. Basically, on my left, the alkalines and Earth alkaline, you have the cation that can occupy the A site. At the bottom, we have elements that can occupy both A or B site, and in the middle, the transition metals can mostly occupy B site. Taking into account that it's possible to substitute a share of the A site cation with another possibly A site cation, or maybe why not a B site cation, or one of the cation which can play any role, then we rapidly come to billions of possibilities with varying amounts of A and substituting A site cation, and the same for B. So it makes it a bit too much for one brain. And by the way, what are the applications that are found for this class of materials? I mean perovskite ones. Among these billions and millions of possible formulations, we can also find hundreds of use. So we can be quite, the perovskites are used for their photo-emitting properties, but also for their chemical reactivity, especially for redox reaction, and they are actually covering the catalytic converters. but also the fuel cells application, among many others like sensors, many kind of sensors. So we have thousands of millions of formulations, as many properties, as many promises, and the possibility of using them in key sectors, and only maybe a team of human brain, but for sure it's clearly not enough. So we need at some point to have a bit more efficient methods to mine this periodic table, also to mine all the scientific publications that have been published so far, and get a corpus of knowledge. From this knowledge, we can have some nice information, but what we really target is finally the property. So up to now, machine learning has been quite used in the field of perovskite research. It was mostly for investigating the stability map of all possible, already attempted or not, perovskite materials. And now it's about stepping one step beyond and try to make true correlation between composition, possibly some preparation aspects affecting one or another parameter, which is not the composition, can be the texture, for example, or the structure, or or some other side property, which is just beside the composition, to understand where all those properties are coming from. Is it a band gap? Where is it an energy level? What it is, and then to try to rationalize and predict the final performances and properties. And this would be really a very powerful tool towards discovering new materials. Once again, I hope we will all learn about this today, but it is really, really a very important step to make, and a very important bridge to build between the composition and the real property, real correlation. That is my message for today, and I'm really thrilled to hear all this nice presentation. Thank you so much, Bernard, for having organized all this webinar, and also thank you, Francesca and Claudio, for having dealt with all the details, all the organization. And I would like to thank you all for your attention. Of course, enjoy your seminar. If you wish to know a bit more on Knowskite projects, there are other kind of materials. Do not hesitate to pay a visit to our website or to contact me directly. With this, I'm finished with a kind of introduction to the project, and I will just leave the floor to our speakers for today. Thank you very much.
Thank you very much, Elise, for this very nice introduction to the project. It is now my great pleasure to welcome Jürgen Spitaler to the floor. Dr. Spitaler is a key scientist for computational materials design at the Materials Center Leoben. The Materials Center is a competence center for emerging technologies, just like the Know Center. He is responsible for atomistic modeling of functional materials and for method development in the area of atomistic modeling. He has received his PhD from University of Graz, and now works as a staff member and group leader for the atomistic modeling group at the Materials Center Leoben since 2012. Jürgen, thank you very much for your willingness to present your work here. The floor is yours.
Okay, Bernhard, thanks a lot for the nice introduction. So let me try to share the screen. Can you hear me well? Okay, perfect. So let's see if screen sharing works. I'm going to full screen mode. Let's see what happens. One moment, I have to change one thing still. All right, can you see now my presentation in full screen mode?
Yes.
Okay, perfect. Okay. All right. So thanks for a nice introduction. So I want to present you today how we put hybrid modeling for materials development into practice in terms of the infrastructure, which is the iPad platform we are building up in a larger research project, and how we do Bayesian optimization based design of new steels. All right. Okay. Okay. This work was done with a series of colleagues from Material Center Leoben, but also from Knowskite Graz. Means these are colleagues of Bernhard's and people from University of Leoben. And the activities I'm showing you today are funded by special funding program in Austria, which are the Commit Competence Centers. Okay, let me start right away with shortly explain what Material Center Leoben is about. So this is Material Center Leoben. MCL is a competence center for materials process and product engineering, which is done in an integrated way, combining experiments, simulation in different ways. We have 180 employees. Traditionally, our strong background was the expertise materials characterization, but we have a lot of state-of-the-art experimental facilities, many different scales and properties. We're doing simulation on many different levels, also combining different length scales. As Bernhard mentioned, my own background is in initial calculation and atomistic modeling, but we have a lot of other methods as well. And we have also started to do more intensively method development, also in terms of simulation, where we are producing software for different kinds of materials properties, also down from DFT codes up to codes which deal with macroscopic materials properties, for example, of railway axles. All right, and then in terms of things that are relevant today, especially Material Center Leoben has started also to dig into AI-driven material science for about 10 years already. We have been applying artificial intelligence methods for areas like condition monitoring of in-service, that means in-service behavior of parts, the prediction of failure, then how to speed up and improve or enable large-scale atomistic modeling using machine learning, and also in the context of finding process structure property relationships, where we have done a series of work and published a series of papers already, as you can see here. All right, so we had already from single project in terms of already that the idea that artificial intelligence is helpful for many or can be helpful for different steps of materials understanding, so to say. But then at Material Center Leoben decided to invest more in this sector and to start up a larger initiative towards how to do machine learning based materials design in a way which works well for us. And this is where we came up with two larger projects. One at the one hand side, the MCXL project, which I'm leading, which is about developing a materials acceleration platform with radically new possibilities for materials development. So this project is about developing methodology, about building up infrastructure, and doing the whole thing in close relation with domain experts for two use cases. That means the design of the platform and how it's structured is already based on input also from use case experts. And then, of course, it's also applied to do materials optimization for two use cases. Then we have a sister project related to the MCXL project called Hybrid 2.0, which deals with the construction of probabilistic hybrid models. I will explain in more detail what this is later. And in this use case, in this model project, we have dealing with two use cases from MCXL, but on top with two other use cases. We have, of course, a strong exchange between the two projects. Now, today I want to focus on this first project because and I will focus on what we do and how we do practical materials development. All right. Since we are application oriented and always have use cases in mind, I want to start also with the use cases. Let me start with the right one because it's close to one of the use cases in your project. It's about perovskites, even though for yet another application compared chemical reactions, and also it's also not solar energy, but it's about lead-free perovskite dielectrics. These are materials which you need for energy conversion. That means they're important for the efficiency. Energy conversion is taking place all along the chain of electricity, starting from energy production via conversion of AC to DC and vice versa, like then from battery to the motor and so on. So this is it's also an important material for green transition. However, today we'll focus on the magnetic seals on the left-hand side. This is a completely different material from the perovskites. It's a metallic material and not ceramic or semiconductor. Then this is really a material that is where we use casting. While for the perovskite use case, we are dealing with thin film production, and then magnetic steels are about mechanical properties, really, which in our case is the yield, strength, and uniform elongation. While for the perovskite materials, we are dealing with the energy density that can be saved in this electric material. And those, of course, the applications are different. For magnetic steels, they are used in the automotive sector for rails and train wheels, seismic anchors, for example. That means the reason why we have these two use cases is that they are very complementary, very different, and this way we guarantee that our platform is really not too much focused on one single use case while still being built up with experts from certain domains. Last, I want to mention the magnetic steels are also very interesting and beautiful also in a sense because they have a very nice rich structure on different length scales. So it's not a uniform material, but it has like a microstructure with different phases involved. On the microscope, we would see a structure like this here with sheaves, sheaf-formed structures, and on the length scale of 10 micrometers. If you go deeper, you will find substructures and like glove-like structures in the sub-micrometer range. This is not just beautiful if you look at it in microscope, it's key for the performance of the material. That means how exactly this substructure looks like. So it will also play a role in the material optimization we're doing. And a few more words on why bainite for building up an artificial intelligence-based materials development infrastructure. First of all, they really have an impact. Maybe you know that materials are production and the whole value chain of materials is responsible for 50% of the greenhouse gas emissions, for example. That means if you do better in producing materials, and steels are a very important material in that sense, you have a strong leverage also for having an impact on the environment. On the other hand, technically speaking, in terms of what we know about magnetic seals, we have insights about quite some about a few sub-properties where we also physical models exist to describe certain aspects of structure property relationship, but it's not a close view. We have also lags there. We don't have a complete model of how magnetic materials form and how the chemical ingredients and the process conditions lead then to the properties at the end. That means it's a perfect playground or maybe a perfect challenge for using hybrid modeling. All right. Okay, so how do we do what we want to do is radically new way of materials design, and of course we use artificial intelligence for that because that is able to do everything, right? So we expect the AI to do the job for us, so to say. But then if we start to think about it, we may realize, for example, that many typical AI methods need really large data sets, maybe millions or billions of data points. So are they feasible for the materials design of materials that we are interested in? And if you have a closer look on how data points look like in our sector, to get a new data point involves many experimental steps. For example, going already for this magnetic steel, you have to put the raw materials together to cast them. Then you have to do chemical analysis to see what the real composition is. Then you have experiments like the electrometer experiments, where you heat up the sample and see how it then deforms. And this is also kind of heat treatment, which changes the properties. Then you have to understand how it looks like on the micrometer scale via methodology like electron microscopy. Then you have large machines, so mechanical testing with huge forces. And at the end, you understand that you have a considerable cost involved in one new data point, which means thousands of euro, and also considerable time that in reality, this really takes weeks to produce as a new material, to produce the samples for different analysis steps, then really get the data you're interested in. So in this sector, we are quite far away from fully robotic automated systems, and data points are really valuable. Also, starting point are really few data points. So the typical situation is here that we have tens to a few hundreds of data points. And this, of course, has a large impact on what methods we can use in terms of machine learning. And the way to go is that we are going is that we use an active learning ansatz, which is used to minimize the amount of training data and to have sample efficiency. That means need as few samples as possible. We're using probabilistic hybrid models in the active learning loop, where we combine physics-based description and data-driven approaches to be optimal in terms of knowledge exploitation. That means we want really to use all available knowledge to be able to handle with the small amount of data points. And I will explain now in the next slides the details of the approach. All right, let me spend a few words on what active learning is about. Many of you probably know, but still I want to use it as a starting point. So if you active learning means that you start from a database, from a data set, a model learns from this data, and as soon as you have your first version of the model, you can predict the properties of new data points. And from this, through this prediction, the model can suggest new data points to improve itself, so to say. That means the model itself suggests which new data points to provide, that it can then be, in order to really find these data points, an experiment has to be done. And these experiments and feeds back to the database, and which helps then the model to improve in turn. And so iteratively improve the model. It's getting better and better. And this way you come with as few training data points as possible to a good result. All right, so this is the active learning loop. What does it mean more specifically if we use it for materials design? In materials, okay, of course, at the beginning, one has to make up her mind or his mind about what exactly you want to optimize. That means you have to define the objective function of the active learning process. Secondly, you have to think about the design space. It means you have to define which chemical elements, for example, to consider. Maybe want to have there certain metals, but also you don't want to have them because they may belong to critical raw materials or too costly and so on. But it's also about the process and process conditions you want to consider. That means like temperature range for thermal treatments, like certain mechanical procedures like forging that you may take into account. That's the second thing. The third thing is a start data set, a data set to start to do the first training of the model. Secondly, so it's also I think I will explain more detail later. We are dealing with data and uncertainties, the special approach we're using, and we're taking into account physical knowledge. How is that done? Before going to the next point here, I want to go into more detail. First of all, we are dealing with probabilistic models. That means we include insertions in data points and in the model parameters. And we can then also, using such models, we can find statistical relationships between attributes in the model. Using probabilistic models enables one to identify regions in the design space with high optimization potential, either because they promise to be good in terms of materials properties already, or because maybe the uncertainty is very large in certain regions, such that you can improve the model by really going to that region and really doing experiments there. So they have attractive properties. However, if you use them still really data-driven way, they need a lot of training data, so they're then still not suitable for our situation. That's why we use probabilistic hybrid models. And then the hybrid models, we combine physics-based description and data-driven approaches. Hybrid models allow for an accurate description from few known data points. And in hybrid models, you can, for example, tune or fit parameters of physical models through Bayesian inference, where you also get uncertainty estimations for these parameters of the physical models. But let me go in more detail about that looks like in our case, and now go for the active learning loop for materials design. Let me explain you the background and infrastructure in more detail of the design process we are doing here now. So now I come really into practice. Now this is the hybrid model we are using for the magnetic use case. This model is constructed by a probabilistic graphical model. Via the graph, the conditional dependence between the random variables involved in the model is structured. That means in contrast to a general machine learning model where all input parameters can be related to all output parameters and by all intermediate steps and parameters. Here we, the experts already structured the connections between different parameters, and via selecting the connections, also removing connections between parameters which are not dependent on each other due to the physical expertise that we have, we can already encode physical knowledge in the model. In our case, the input is the carbon content of this steel type, the metallic alloying elements, the process temperatures. And going through all these process steps and parameters, we end up then with the final properties that we are interested in, which is the real strength and uniform elongation. Okay, so this is the model where physical and the connections where physical insight comes into play. The second aspect are the submodels we're using in the model chain. You can see here that in the model chain we are using, for example, thermodynamic models to determine this Benedict star temperature, which is the phase transition temperatures, the concentration of retained austenite, which is a special subphase of these Benedict steels. We are using phase transition models to find the phase fraction of bainite in the whole material. Then there's another phase also appearing in the context of Benedict steel, which is called martensite. Then there is a certain temperature where this phase starts to form, and so we have another model for that, which is a physical model, and still another model for describing the formation of a certain kind of grain boundaries, the high angle grain boundaries, which and then in turn impact on the mechanical properties we're interested in. So this is the second level where we introduce the physical knowledge in the hybrid model, that we have submodels which are physical models. All right. So now come back to active learning loop for material science as we're doing it after having started, and we have now constructed the probabilistic hybrid model to do this accelerated materials design. We can use that now for doing Bayesian optimization. That we can, training that model to the first data set, we can calculate expected improvement for millions of data points, and then find out which one are most promising to optimize the design procedure. It means then a few data points suggested by the model for further characterization, for the experiment. That means these data points are then typically produced in the sense that the materials are produced, samples are produced and measured and characterized. Alternatively, they could also be characterized by high-level costly simulations like ab initio simulations. As soon as they characterize, you will understand whether this new data points already fulfilled as a design criteria or not. Normally they don't. That means they go back to the database. That means new data are added to the design space. The model is retrained on the better data set and new points are suggested. And in this materials design process, we typically go through this loop a few times, say 2 to 5 or 7 times. We then really come to a good satisfactory result, to have the optimized material that we wanted to have, or at least the best material in the science space we have considered. All right, so this is now schematically what we are doing. But for doing so, one also needs infrastructure because we are dealing with algorithms, with programs, with data. And in order to go through this loop efficiently, you have to have a good infrastructure also for people to use the methodology, to deal with the data, and also for the algorithms to be able to access the data they need. And for doing that, we have been building up the ALPMAT, the active learning platform for accelerated materials development. Here I want to show you how it looks like and how it covers different aspects that are needed to run the active learning loop. Okay, first of all, we're dealing with data. So the central element here, it's called IRODS. IRODS is a data management system, actually an open source software, which is quite versatile. It's able to deal with any kind of data. It can be text-based data, it can be JPEGs, can be any kind of documents or movies and so on, any kind of data, which is important because also experiments produce different kind of data. And IRODS also enables the possibility, or has the possibility to provide metadata for any kind of raw data set that you put there. Then, so this is the data backbone, so to say, and then we have different calculation services, software programs that interact with the database. First of all, we have a graphical user interface for data management, which where one can search a database, have a look at metadata, also add metadata, share data between persons, and so on. Then we have a data model implemented, which is also important for the specialists to work on the data, and I will present that also in an extra slide what it means and what it does. Then we have a graphical user interface for data ingestions for different methods, which are specially designed for the use case methods for the use case we are using at the moment, and to be efficient for the operators to ingest data from the involved measurement methods into the platform, where we have dictionaries for the metadata that are needed then for this any kind of measured data, such that we will come up with fair data then on the database. And then also we have a service called literature tool, because as in any research, literature is a very important starting point. So it's important to be efficient to find the relevant literature, but also to extract the data and make them machine readable and fair as efficiently as possible. And this is greatly supported by the literature tool. And last but not least, and especially important for company partners, is of course that how you deal with data privacy, data access, and so on. This is done by the account management system. You want to be sure that only people are allowed to access the data that should really that you want to have the permission also to do that, and you want to have the control of every part involved over the data and how they are shared. And so this is handled by the account management system. All right, this is the level of database, which is very important for materials design process, the starting point. Second aspect is the AI-based model. So if you're working with database approaches, first of all, of course, they also have to have access in the data management system. Then we have plotting tools where you can get a quick overview of the data and the structure of the data, and also maybe outliers and trends already. But then the most important service is the data analysis, which is actually Jupyter Hub. That means Jupyter notebook system where you can run, amongst others, Python scripts. And in our domain, Python is like the most important programming languages where models are implemented. So this is where actually our hybrid model is run then on the Jupyter Hub, and this can access the data in inroads, of course, also. Again, we are also like connect to account management. And finally, we have, when it's about experiments, we have customer services to upload experimental simulation data and automatically also extract metadata from these. Oh, it's a little bit late in time, so I should be a little bit quick. Okay, let me mention shortly that then data models are also important. That means we have a representation of the connections between the experimental methodology, how this flow of samples, how they're cut into subsamples, how the state of samples change, for example, in heat treatments. So we have the whole sample workflow and processing workflow represented in a data model with suitable software solutions. And so if you work on the platform, if a specialist works on the platform, he can really then ingest data by making use of data model and saying, for example, now I'm uploading data for the microstructure from light optical microscopy, and click here and upload data there. And then he will also see how the sample he has looked at is connected to other samples and how the history is. So that's a very important point for the practical usage of data on the platform. All right, so but now should really come now to the final section about how we do how we did Bayesian optimization for BNeT-XTs with active learning loop, how well that worked. Previously, I have already shortly presented you the hybrid model that we're using for that case. Now let me show you how that worked. So it's a multi-objective optimization with two objectives. First, of the one hand side, we want to maximize the yield strength, and the other hand side, the uniform elongation. You can see here the starting data set, which was about 50 data points, among 30 from literature and 20 from MCL. And in the dashboard lines, you can see the old Pareto front, which was there from the training data. So we built up, we have used this hybrid model that I have shown you before, and did a Bayesian optimization to suggest new data points. In this first iteration, and new data points means new chemical compositions together with their thermal processing conditions, this isothermal holding temperature. And for this, they were really synthesized and characterized in terms of heat strength and uniform elongation. And actually, we were really, really happy that already the first suggestion with the model with a lot of uncertainty still led us to new points beyond the old Pareto front, which, as you can see here. How did these points look like? You can see here the chemical composition, like steel is, this steels contain quite many ingredients already. So you have a different content of silicon, for example, manganese and so on, different processing temperatures. Actually, one of the samples was then rejected because it turned out on the microscope not to be a magnetic seal, but other kind of seals. It was outside the design space, so we don't consider it. But then we had 4 out of the 5 suggestions were beyond the old Pareto phone. And we could also already learn here how processing conditions also change the properties. You have the sample BO5 with this chemistry here. You can see here the cooling speed. So you've in the thermal treatment you cool down with different speeds. Here with 0.2 degrees centigrade per second, here with 0.15, and you see how the mechanical properties of this point change in dependence of this processing parameter. And here for the other sample, you have different isothermal holding temperatures. And again, you see how, for example, the uniform elongation here changes really if you vary this processing parameter. All right, so we were really happy to be able to improve already in the first iteration. This is ongoing work, so the second iteration is close to finalization. So we're really optimistic to go much farther even in Sotir's properties and really have now a tool at hand to put materials development into practice using hybrid modeling. This is I'm coming to my end. Okay, artificial intelligence offers radically new possibilities for materials design, but you have to know to use the right methods of artificial intelligence, which are adequate for the situation that you have with very costly data points. So that means we do this materials design take into account sample efficiency. That means we use active learning to be able to live with as few data points as possible, and we use probabilistic hybrid modeling where we have optimal knowledge exploitation. We have built the infrastructure for doing so and have applied it to the use case of magnetic seals, where we have already first promising results. So thanks for your attention.
Thank you very much, Jürgen, for a nice presentation. I guess we can take one question now, but postpone the remaining questions to the discussion period at the very end. So are there any questions from the audience? I'm quickly checking the question answers. Yeah, Andreas Hauser, next speaker is having a question. I think you can unmute yourself and ask because you're allowed to. Please go ahead.
Okay, thank you. Yeah, thanks for this interesting talk. I was just wondering if you could briefly comment on like bottlenecks or in general the hardware equipment that is involved in this AI machinery that you presented.
Okay, the hardware equipment, we have a workstation, not even with GPUs, but just the CPU, I think with how much? With about 20 cores that has been used for training this model that took, I think, 1 to 2 days. Mm-hmm. Now we have moved, but then at some point we've moved to the Vienna Scientific Cluster also for doing training. So it's it costs some time, but for example, compared to the initial calculations we're typically doing, it's still little effort, and there would be a lot of room for improvement also using GPU technology more intensively. So they are not extremely resource intensive, so it's a moderate resource cost.
Okay, thank you.
Thank you very much, Andreas. Well, then thank you once again, Jürgen, for the nice presentation. Thank you very much, much appreciated. Please stay in the webinar. We are not done yet. We're waiting for your important input also to the roundtable discussion at the very end. But now I think it is my pleasure to announce the next speaker, which is Andreas Hauser. He holds a PhD in physics from Graz University of Technology and a PhD in philosophy from University of Graz, where he focused on logic in AI research. He then was a postdoc at Massey University in New Zealand and at University of California in Berkeley, and is now an associate professor at the Institute of Experimental Physics with a focus on computational chemistry and molecular physics. And I'm very much looking forward to his talk on machine learning of energy structure relationships. Andreas, please take it away.
Yeah, thank you for the kind introduction. I have an issue here because I'm not so familiar with Microsoft Teams, and it tells me now that I have to close the app in order to get. Let's see if this is. Yeah, to allow for screen and system audio recording, but maybe it's maybe this is working. I'll just try to share.
Andreas, do you see the share button in the upper menu on the right? Can you see it?
Sorry, I was kicked out for a moment, but now I'm back. Yes, share. Then
you can select a window or the entire screen.
Oh, yes, yes. Okay, then I'm clicking. You need to go back to the window you were sharing to resume. Okay. Is this now working?
We can see it, yes.
Okay, perfect. Okay. Yes, so sorry for the trouble. Good afternoon, everybody, and welcome to my talk. I'm very happy to present research that has been done in my group. So I'm really grateful to the organizers to have the opportunity of presenting our work, and I have the title Machine Learning of Energy Structure Relationships in Mixed Metallic Clusters. But I would like to use this opportunity and give a talk that is split into two parts. The first one will be our previous machine learning group activities, because I would like to show you several ways of how we thought that machine learning could be useful in this field of material science with computer support and modeling in general, and then dedicate the rest of the time to this specific topic of energy structure relationships in metal clusters. So the first part, so it's a routine task in computational chemistry to have this structural or this link between structures and energy, so structure-energy relationships. And these systems that we're dealing with are, as was already mentioned, notoriously complex to solve, and they need a lot of time to get often energies or properties at one specific geometry, so meaning for one specific structural arrangement of, for example, a single molecule or a specific metallic cluster. And so we refer to this as the potential energy surface, which is the energy of such a system, in our case, typically the electronic energy of this many-particle system as a function of internal nuclear coordinates, like so everything like bond length or angles, or, for example, Cartesian coordinates. And so the energy is basically a value that you get by solving a complicated differential equation. It's the Schrödinger equation for the electrons that are involved in the system for this given molecular structure. And so if you calculate this energy now in dependence on the various internuclear degrees of freedom that you have, you get this potential energy surface, which is a high-dimensional scalar function. And obviously, you are interested now in extrema points on the surfaces, so minima and typically also saddle points or transition states. And so most of the time, people are first of all interested in finding the global minimum or the equilibrium structure of some molecule, or in our case, a cluster. But it's also interesting to look at transition states that link this minima, because any type of chemical reaction can be described on a certain potential energy surface. If you think about it this way, you have the reactants, which are basically simply a geometry that is one specific point on your potential energy surface. And then you have the product states, or the product, which is another point on the very potential energy surface of this whole system. And in order to describe the chemistry now, you would like to find this minimum energy path that connects your reactant state with the product state. And this goes over a barrier typically, and you have to find this minimum energy path, which is another complication, because you have to evaluate many single points on this potential energy surface to learn about it and to make a better prediction in a more or less iterative way, because it is too high dimensional to do a brute force scanning in all of the degrees of freedom. And so you need something like machine learning to improve or to take a maximum information out of what you have already with your data set and improve improve from one step to the next through information that you have gathered from steps before. Transition states are relevant in that they are defining the kinetics of a reaction, right? If you have an equilibrium state, product state, and then the reactant state and the product state, the energy difference would determine your thermodynamics. Is the reaction is it exothermal, is it endothermal? But in order to gain information on the reaction speed, you will also need to know the energy of the transition state with respect to these minima. And so we did contributions, or we provided contributions for geometry optimizations, finding these minima, but also to find these saddle points. And so this transition state search here, we made a contribution to a algorithm that is called the nudged elastic band algorithm, because if you think about the potential energy surface is something we can still imagine in our brain, like a two-dimensional surface, like a landscape, and you want to go from A to B, from one valley to the next. It leads over this saddle, and one way to find the minimum path would be to take a piece of rubber and then put it onto this landscape, and then the rubber would snap onto the minimum energy path, more or less. And this is translated into this nudged elastic band algorithm, but this process is an iterative process. At first, you say this is the starting point, this is the ending point, and in this abstract space of coordinates in which your potential energy surface is sitting, you make a direct connection from this starting geometry to the end geometry, and then you separate into small steps. These are called images. And so you have at first a very naive assumption of how the reaction takes place to go from A to B. But you calculate now the energies and also the derivative of the energy with respect to displacements of the atoms. So you get some information on the actual force that acts on these atoms. And based on this information, you are continuously updating your pathway from one step to the next. And our idea here was to do this nudged elastic band calculation, this algorithm, on a surrogate surface that is using information from the first set of images that you calculate. You try to create a surface that is very cheap to generate, and on this surface you do the full nudged elastic band algorithm until convergence, and then it tells you where to place the next images, or in other words, where to move the rubber band to on the next run. And this way you get a new selection of data points that you have to evaluate in order to improve your result. And then you evaluate again on the real surface, because although it is approximative in the way that we have a surrogate surface, eventually the surrogate surface should converge to the exact surface and should give you the exact result for the transition state and also for the whole minimum energy pathway. So these were things that we did with respect to this potential energy surface concept that is appearing a lot in molecular modeling or in atomistic theories. Now, another contribution that we made was with respect to the actual methodology of calculating the electronic energy. We've heard it in the previous talk already. This is one of the many tools that are applied, or density functional theory. And there is one variety that is less common because it is still not able to compete with the standard technique, which is cone-sham DFT. The original idea is orbital-free DFT. So density functional theory is in contrast to what I've been telling you before, where we solve the electronic Schrödinger equation to get the wave function of this n-electron system. Here we are only trying to get a connection between the electron density distribution, which is a much simpler mathematical entity. It's just a function of XYZ coordinates, and this density has been proven by Hohenberg and Kohn, this direct mapping onto the energy of an electronic system in its ground state. And so this makes it so much simpler because it is a scalar function of 3 coordinates instead of a wave function. It is a very, very complicated many particle description of this quantum system. There's just one issue with this modern cone-sham technique, that is the standard DFT procedure. So the cone-sham DFT makes a meaningful, or makes a good approximation of the so-called kinetic energy of the electrons based on a picture which is actually borrowed from wave function theory. It is using the concept of orbitals. That is something you only need in wave function based physics. The concept of orbital, and orbital can be thought of as a effective single electron wave function. And so it takes this concept in order to get a reasonable description of the kinetic energy contribution. But this means it reintroduces the orbitals, which makes the calculation much more complicated. And so our attempt was to find a mapping of this kinetic energy expression, the kinetic energy of the electrons, to the electron density distribution, and to use a neural network in this case to learn this mapping for a small system, and then try to extrapolate or learn and use it also for many electron systems. So this is just to give you a feeling. We really tried to see where machine learning fits into current problems of computational chemistry, and so this is where we made our small contributions so far. And now I come to the second part, which is the actual title of this talk, the modeling of metallic nanoparticles. And here the problem is the following. We are interested in phase diagrams at the nanoscale. So here on this slide, you can see, for example, platinum gold phase diagram at the bulk. And you see it's already pretty complicated. We have on this axis the temperature, and on this axis we have the ratio of gold to platinum. And for example, at this dashed line, it would be 60% gold, 40% platinum. And at, say, 1300 degrees Celsius, you're in a phase where you are liquid plus some solid phase, and this is the picture below. You have a platinum-rich solid phase, and you have a gold-rich liquid phase. And if you cool this further down, you go into an area where you have just one solid phase, and then you have 2 of them. As you can see, in the bulk, this is already pretty complicated and needs to be evaluated in a combination of a lot of experimental measurements and probably meaningful theories also from physics theory. Now, if you go now to the nanoscale, things are getting even more complicated. So our question is, how does the phase diagram look for a platinum gold particle? And here you are entering a regime where you have an entirely different surface to volume ratio. So surface effects, like as a fundamental perturbation of the actual bulk system, the interface itself is dominating the energy. So surface energy plays an important role. Depending on how you cut, you have different surfaces as an interface, and therefore different energy contributions. And then at this size, different crystal structures are to be expected depending on the actual size of your particle. And so this means that the phase diagram at the nanoscale is also dependent on the particle size. If you look at one specific particle size, we are immediately realizing that there is an astronomically large number of isomers that are possible with energies that are some can be close to each other or significantly different. So you need a clever strategy of how to explore this gigantic space of parameters. To show you that this is still a very topical problem, it was just recently an article in Nature Nanotechnology where rhenium gold was studied, a combination that has strong demixing in the bulk. It has no miscibility, but if you go to the nanoscale, you have a continuous transition from a phase-separated situation into an alloyed situation. So here, this is what people tend to call Janus particles. It's two-phase. There is basically no mixing of the two phases, and then at a certain size, you have real alloying that is here. So in order to describe this, people are dependent on high quality models that really deal with the electronic structure of this problem. So we have to go to DFT, sometimes even beyond standard DFT approximations, and they are very costly. So the single point evaluation is already very costly. So what are the alternatives? And this is where now machine learning comes in, because there is a lot of knowledge in the community already of how to describe energy, the total energy of such a system, based on the geometry of your cluster. And there were attempts now to improve the models that have been used for decades now by additional fine-tuning through machine learning. And this is something that we are investigating at the moment. How can standard models that are used or have been used a lot in the past be systematically improved through machine learning techniques? Because we would like to keep in some of the physical knowledge. As you will see, this plays simply a role because your data selection that you're using for this calculation is often not sufficient to make the predictions of structures that you might encounter. And so this is simply not fully covered in your data, and you would like to have this captured at least through physical knowledge that is encoded in your setup. So before giving you our approach, what comes to mind is force field models, for example, as they are used in chemistry when you are dealing with structures of organic molecules, for example. And here there's a straightforward idea of saying that the actual interaction of this many particle system, which is basically all electromagnetic interaction, often just a Coulomb type interaction, can be mapped or can be approximated via a simple ball and spring model, a mechanical model. And then you introduce energy ingredients for stretching, for bending, for torsion, for out of plane energy. And this is something that works pretty well to get an approximative solution for a potential energy surface in molecular structures. But this is not working for metallic systems because you have a totally different type of binding. You have metallic bond, you have very high coordination numbers, you have the same electronegativity, therefore electron correlation plays a fundamental role, and this is not captured in these force field models. A brute force approach, and this is something that I'm mentioning because there was a big breakthrough, but this is now almost like 20 years ago. It is still something that people refer to as the standard Bella-Parinello type ansatz, a brute force neural network approach, where you say, okay, I'm interested in the energy of this say 15 atom metal cluster, and I'm approaching this by saying the total energy is the sum of energies of each of the atoms, and I'm evaluating this energy based on the local environment of each of these atoms. So I'm introducing descriptors that translate a certain environment into input vectors for my neural network. I'm giving this to a neural network, and I'm obtaining a specific energy for an atom surrounded in a specific way by the other atoms. Other atoms might be atoms of the same element type or of the other one or of a third one. Then it gets really complicated if you have many of these combinations going on. And you are having descriptors that tell you this distribution with respect to the radial dependence, but also with an angular resolution. So this is shown here. And so you go from one atom to the next. This gives you different environments and therefore different energies. And you calculate the total energy as a simple sum of all these energies. And this is how you train your network. You give DFT energies for the whole 15 atom cluster, for example, and you make it reproduce basically this energy based on the sum of the energies that are evaluated for each of these fingerprint environments for each of the atoms. So this is a brute force approach because this is fully uninformed and this is working if you have huge amounts of data, because the typical network size that is involved in this type of ansatz has hundreds of thousands of parameters, right? So you need a lot of data to actually touch all of these parameters in their nonlinear optimization that is going on under the hood of your neural network. And so the alternative for our case is something that stems from the community, which is called embedded atom model, which is, and this is a funny thing, it has this concept of it's a crude simplification, but it is something that has been used before in this community, namely to say the energy is the sum of the energies for each of these atoms, like I said before. But here, the energy contribution for each atom has three basic building blocks. One is a typically repulsive pair potential here in blue, and the second term has two parts. One is the so-called pair contribution to the density term, so where you basically have a description of the local nuclear density distribution around your specific atom that you're interested in. And then you have a nonlinear function that translates this density into an energy contribution. This is called the embedding function. And so this is all physically motivated. And these functions, for example, the embedding function or the pair potential, there are certain analytical expressions that stem from certain models. And for example, the embedding function is typically proportional to the square root of the density. And so knowing this, we would like to use this information now and try to improve it. We go into these contributions, each one of them, and make it a bit more flexible by introducing a neural network. For example, we are playing with the embedding part. We still keep the square root of rho to have the correct limiting behavior, but we make it a bit more flexible by making it also affected by a neural network that is trained. Or we are modifying our density approximation, or we are modifying both of them. And I am not sure how much time I still have.
Let's say 5 minutes.
5 minutes. Okay, thank you. Thank you.
Yeah.
Mm-hmm. Okay, thank you. So these are the models that we test, and then we need the data to train our network. And as we've heard before, this is the crucial part in computational chemistry. Each of these data points is typically very costly, and you have to be clever in how to generate a data set that provides you with the information that is needed for you to make the correct predictions in the regime that you're interested in. So in our case, we would like to have a sampling of this parameter space that is wide enough to really cover all possible isomers that might be of relevance, but also stick with structures that are still meaningful. Obviously, if you have two atoms getting too close together below half an angstrom, this is completely useless, because this is happening at temperatures of, let's say, several thousands of Kelvin, completely irrelevant for any standard physics. So what we did was short ab initio molecular dynamics calculations So you give the system a certain temperature, in our case 2000 Kelvin, to have enough movement, and then use, in our case, density functional theory to evaluate energies and forces and use this as an input. In our case, since we are interested in these mixed clusters consisting of, say, 2 different metal types, we go from a size from 10 to, say, 150. So really in this regime where it is a more atomistic, and you can still see fundamental effects if you just go from one size regime to the next. If you just add a few more atoms, the cluster physics might be totally different. And so this is our data set, and then we do the training with a loss function that is considering differences in energy as well as in the forces, and we get these results. I guess this is less important, and it's still ongoing work. First, we take this second moment approximation to tight binding as our reference. So we take this model, this historical model, and we fit it to DFT data points, and this is our reference, because this is telling us, okay, this is known information, so this is maximum use of the information known by the community, basically, that went into the structure of this model. And with this we do our calculation, and we get eventually, after fitting these few parameters, to a certain predictive power. And then if you do now, if you throw in your machine learning ansatz, you can improve on these results, which is a necessity in terms of mathematics, because you are having all of a sudden not just say 12 parameters, but you have maybe 1,000 if you do an embedding, if you change the embedding function, and you can reduce your error or improve your predictive power. With density, neural network answers for the density, you can improve it even further, and if you combine it, it gets down to the best we had so far. But this is sort of obvious, because you are buying this with increase of parameters, and you have now like 2,400 parameters. So this is again a highly nonlinear fit. You need a lot of data to make a meaningful training here. So this is ongoing work, because there are 2 things that we would like to learn. First of all, what is the physics recovered by the machine learning that we put in? Can we actually, if we give it a certain flexibility, also retrieve the details or the thoughts that went into the development of something like the second moment approximation to tight binding through human brains in the last decades? Is this something that we can reproduce? Can we, for example, also see that the embedding function has this square root dependence, and this is the best way of approaching it, and not, say, some other analytical dependence? So this would go into a network description that uses symbolic terms. So this is something we are also interested in. And to conclude this talk now, another interesting finding, just to show you what are the limitations of such a neural network. If you let the network learn on systems that consist of 10 to 150 atoms in this mixed feature of platinum and nickel, for example, what's the prediction of these networks for the simple diatomic molecule platinum-2, nickel-2? And to make a long story short, if you take the fully uninformed system, Bella Parinello, so this brute force network, it is not able to reproduce the DFT potential energy surface, which is in this case a potential energy curve, the dashed line. It's completely off. Now the physics-informed models are already giving correct behavior. After refitting, just refitting it to the DFT data, we get the correct trend. This is the orange lines here. You see platinum-2 has the deepest well, and then it goes higher till it is N2. So this is already captured by the fitting of the SM-ATP model. And then with NN improvement of the embedding function or the density, you get a bit closer to the physics. So there is some physics that you can recover, but interestingly, playing with the embedding function keeps this behavior that platinum is deepest, now the green curve, and nickel is higher. But if you play also with the density, you sort of destroy certain features that have been already recovered before. So you can see you're adding flexibility, but at the cost of your ability to stick with hardwired physical knowledge about the systems. And if you go to larger systems, like those that are actually in the data set or even bulk, then these models are behaving as they should. So yeah, with this, I'm at the end of my talk. I thank you all for your attention, and I'm happy to take any questions.
Andreas, we have a question by Parul in the chat. So if we consider Con-Sham instead of DFT, how can we take account for exchange correlation since Con-Sham is not suitable over here due to the presence of localized 4F and 3D electrons in perovskites?
Okay, so our contribution is dealing with the kinetic energy contribution to the overall expression. And if this works, it can be combined with any type of exchange correlation functional at hand. So it is basically our wish on the long run to have orbital free density functional theory available for any of the known functionals, including those that are known to perform best for perovskite structures, for example.
Thank you very much, Andreas. So I leave the stage to Bernard and Elise.
Thank you very much, Andrea. Thank you very much for your presentation. Is there any other quick questions from the audience that we can address right now? If not, then I think we can thank Andreas once more for his very nice presentation. Thank you very much also for the kind introduction to the work of your group. This was extremely interesting. I now just trust on the fact that they are on time, and since my colleague Sean has already activated his webcam, I think we are prepared for the second half of today's webinar. And it is my great pleasure to announce Sean Cody, who is a data scientist here at the Knowskite Center. He has completed his master's studies in the field of computer science, where he worked on stellar classification with photometry data. He received his master's degree earlier this year. He has previously worked in research and development in the field of mixed reality, and is now working in the broad field of machine learning at large, and also reinforcement learning. And this will also be a major topic of his presentation. So, Sean, the stage is yours.
Hey, thanks. You can hear me, right? Okay, cool. Next question. Can you see my screen?
Yes.
Yeah. Okay, cool. Okay, yeah. Thanks for the introduction. Today I'll be briefly talking about reinforcement learning in materials design. And we have already sort of covered some supervised learning approaches to materials design. And the question really was, when we did our research in the field of basically perovskite optimization and in potential energy surfaces, basically we came across reinforcement learning and wanted to basically discuss a couple of papers. So this presentation is aimed at materials design experts. So I'm not going to be going into the details of materials design, but rather focusing first on giving a bit of an introduction to reinforcement learning, one prominent algorithm, which also comes up in one of the papers which I'll present. And basically one algorithm will be introduced, and then I'll present two very, very cool papers, which I think will be quite relevant, at least to our research, our work in materials design in the field of perovskites. So what exactly is reinforcement learning, and how does it actually fit in? Because we've previously heard in the previous lectures of supervised learning approaches, for example, Bayesian optimization also, and really that would be one of the three main types of machine learning, if you can sort of categorize them as such. And This would be if you have labeled data. So for example, over here, we'd have red points, blue samples, and you want to generalize to the unseen population. And based on these labels, you have a training data set you train, and you learn a decision boundary with which you can then make decisions for unseen samples. So this would be supervised setting, and the unsupervised setting is, for example, in this case with the 2D points, you would basically perform clustering and group feature samples according to similarity of features. So in one case, you have the labels of data on the left-hand side. In the middle, you have data with no labels. So what exactly does reinforcement learning slot in? The setup is a bit different. So it's not concerned necessarily with the data sets per se, but instead you have an interactive environment and you have an agent which interacts with an environment through taking actions and receiving rewards. And this is best seen, I think, in games where, for example, you have a score and you try to optimize your long-term reward. And you do this by essentially having an agent, for example, a robot in a room, which would be the environment, and you can take an action, for example, walk left, walk right, go straight ahead, but want to walk into walls. So you can punish it if it walks into a wall by giving it punishment or negative rewards, so a negative value. And basically, when you take this action, you put the environment into a novel state. And really, the agent over time is supposed to learn how to take, given the current state, so for example, the current chessboard or the current state of this game, Atari Breakout on the left, in order to make an action, for example, to move this paddle with the action left or right, depending on where the ball actually falls. So the idea is through interaction with the environment to maximize the long-term reward. And this brings me to the algorithm, which I'm briefly going to show. And essentially, as I just said, the goal is to maximize future discounted reward at time t being the current time step. And yeah, basically there's a more simple, not a game this time, but a more simple MDP structure, which is a Markov decision process. And it's the underlying principle of reinforcement learning. And you'd have, for example, here, state 1, state 2, and state 3. And you can take action 1 or say action 2 in state 1, which puts you with a certain probability into a different state. And if you know this MDP, you can iterate this and assign a value of the reward which you get for taking a action in a given state with a certain probability. It'll bring you to a different state, but at the same time give you a reward. And you don't want to be nearsighted in the sense that if you, for example, had a chessboard and you could trade your queen, for example, for a pawn, but it would put your queen in a very difficult position and you might actually lose that next turn. So you would want to actually plan ahead. And this is what reinforcement learning does. So for Q learning, let's start off by first defining what we call a state action function, where this function basically, given a state and an action, gives you the expected return GT given that state and action. And we can formalize this with the discount factor, which is maybe the ambiguous part of this goal up here. And we basically do this to entice the algorithm to actually move to states which give high rewards. And it's not that important for now, but essentially if you had a positive reward, you could permanently iterate in that state. And since this is a sum to infinity, you will always reach infinity with a positive reward. So we would like to discount this. So with each time step into the future, it is less valuable. Right, and in that regard, we can also take this theoretical example where we have the optimal state value function. And if this was the optimum, we would be able to estimate the recursively define this and estimate that the action that maximizes the Q function in the next state is actually the perfect description of our total return. Right. So we can actually reformulate this, and when we want to get this GT, so the return, this is an unknown quantity since we can't actually, we don't want to try every single option. in an exhaustive search. But what we can do is Monte Carlo sampling. So we can, for example, play a game, and at the end of the game, every state you've taken through step you've taken through time, you can assign a certain value to that. And we can essentially do the averaging, or this GT, estimated through Monte Carlo sampling, and at the end we of course average. And this can then be rewritten to incremental averaging. And when we generalize this weighting factor, and you're just gonna have to trust me on this, because the equations sort of grew out of proportion, so I simplified this part here. But we arrive at the following equation. So the current state action value is the current state action value plus plus a, let's already call it learning rate, but a factor alpha multiplied by the GT minus the current value. And with temporal difference learning, which is basically when we do this only one step into the future using Markovian property of 1. So instead of being conditioned on all of future states, or all future states being conditioned on the past states, we instead say, okay, it's sufficient to know only the previous state. And by doing this, we can rewrite this GT as the current reward plus the discounted future reward of the next state. And the Q function currently is a bit ambiguous, and this already in the next bullet point is listed as the Q network, because we can use a neural network to approximate this Q. So as input, we would give it a state, an action, an action, and receive basically a value for how good that move would be. And yeah, by training this essentially, and you can already see in this temporal difference learning, this looks quite a lot like a gradient update. And in fact, we can rewrite this as the reward, or the gradient then to impact our loss function. The discounted maximum, or the action that maximizes the Q function, we get this value of the next states and the difference to the current state. Right. So if we have the optimal Q function, we can then proceed greedily and essentially pick the next step that will give us the best reward. The only issue is, while training, we also want to explore, not just exploit the search space. And I've got this memo here. Basically, you can find the small diamonds here. And if you continue searching here, though, without ever going broader and looking at other options, you might actually miss this pretty big reward in a future step. Therefore, we actually have an epsilon value, so we don't always act greedily, but initially, and usually you reduce this over time, but initially you have a lot of exploration, and you try every now and then with a certain probability a random action and see how well that actually goes. And this is only done in training, usually. Yeah, now the big issue with the neural network and why deep Q learning works, though, is that as you can see, updating on or moving the current state closer to the next states, well, it makes sense in the sense that a winning board of chess, for example, is also like the step before, or the chessboard before winning is also a very good state to be in. So getting there is also supposed to be good. The only issue is that these states are going to be highly correlated in value, at least. And to avoid this correlated data, what has been introduced is an experience replay buffer. And it's essentially a memory that stores transitions, where transitions are the current state, the current actions you took, the reward, the next state, and the next action. And by storing this and using basically these transitions by randomly sampling from this buffer or memory you have, you can do mini batch updates. And this basically makes deep Q learning more stable. Right. With that out of the way, maybe this is a good point to basically say why we have actually considered reinforcement learning to be quite a relevant topic to investigate. And it's because we found that Bayesian optimization, or classical approaches, according to some literature, falters in, or can falter in, very high dimensions, or when you have large large search spaces. So with that, we actually looked at how reinforcement learning has been applied to potential energy surfaces and how it can actually find the extrema, so identifying global and local minima. And we found this paper, which is really, really nice, where they use, and this is a different algorithm, it learns the policy directly, but everything else should be easily transferable from what I've said. So the authors used deep deterministic policy gradients. And this is essentially really learning the policy, how to actually move to this global minima. And they also investigated a hybrid DDPG with the goal of finding these points. They looked at the Muller-Brown potential energy surface in 2 dimensions, and they also conclude that this can be done in, or they believe this can be done in higher dimensions, but for the sake of argument, they've focused on only 2 for demonstrating the potential. And what's pretty cool is they used 2 rewards, of which the first one is only the difference in energy between the current and the next state. So your agent takes an action, and if that action brings you into a better, gives you a better value, of potential energy, then that's a positive reward. If it puts you in a worse one, that's going to be a negative reward. And they also looked at a second reward, and that's basically taking into consideration also the distance to the currently last known minima. And very interestingly, this reward engineering helped quite a lot by incorporating this physics knowledge. So the second reward performed much better and actually stopped the algorithm getting stuck in certain saddle points. Or I think maybe was it state transitions? I'm not sure. But and they also, for the hybrid DDPG, the big difference is that when the agent took bad steps, so got a bad reward after I think 3 or 5, I'm not sure on the exact value what they used in the end, steps, then they, instead of taking a random action, they actually gave it the action to move into the negative energy direction, which is what you can see here on the bottom. Right, and what they found is that the location energy inspired reward performed much better. And also that guiding the actors through physics essentially allowed it to converge much faster. And here's 2 results. It's a bit hard to see, but I had to fit it on the slides. But these points here are essentially where the episodes ended. And you can see that there's a lot more in the actual minimas, or global minimas, and you can also see the average reward nicely converges after already approximately 200 episodes. Right, the conclusion the authors drew was that reinforcement learning seems to be highly applicable to actually finding these potential energy surfaces. But one issue we found when wanting to apply this to our research is that the Muller-Brown potential energy surface is known. And if it's not known, we would have to basically generate these this data points. But instead, it's very common. We have a very common setup, which is essentially we have data. So laboratory data, but not this experimental setup where we can actually get this data on the fly. So this actually led us to find this really, really cool paper, which was only published 2 years ago. 2 months ago, sorry, 2 months ago, not 2 years. And it's the compositional design of multi-component alloys using reinforcement learning. And the goal they basically had was to design a phase change multi-component alloy with the highest transformation enthalpy. And the issue they ran into very quickly was that the search space became intractable with increasing alloy elements. And this is where they say that classical approaches such as Bayesian global optimization falter. And one example is, for example, if you have 10 components, you're going to have 10 to the power of 18 possibilities for these alloys. Right. Now they had a similar setup where they had this data, and their idea was to build a surrogate model for the reinforcement learning agent using this lab data and have the surrogate model act as the environment for the reinforcement learning to interact with. But yeah, the problem is that laboratories don't usually give rise to large amounts of data. So the surrogate model wasn't very accurate or not accurate enough. And the solution they came up with was to introduce a feedback loop to iteratively refine the surrogate model. And this is briefly shown here. And they have an inner loop where basically the reinforcement learning agent takes an action, starting with titanium and nickel, and basically changing with the action the composition of the nickel. And essentially, the enthalpy is then provided as the reward from the surrogate model, which is prior to this experimentation fit on the laboratory data. And then they add another element, essentially copper, and iterate this for 5. So an episode is 5 iterations in this case. And once the algorithm converges and no better rewards are gained by the reinforcement learning agent, that's when they go to the outer loop and refine the surrogate model by looking at which areas or which compositions did the reinforcement learning agent suggest with once it's converged, and take these and basically in the laboratory performed material synthesis and characterization and fed this data back into the surrogate model, refined the surrogate model, retrained it, and performed the inner loop again with the reinforcement learning agent. And yeah, again, reiterating that the reward was the enthalpy, or delta enthalpy, the change in enthalpy provided by the surrogate model. The surrogate model itself was a Gaussian process trained on elemental features, which were obtained via feature selection. So maybe starting from the bottom here, the features of lowest uncertainty were chosen after removal of highly correlating features using the Pearson correlation, and also using gradient boosting and looking at the relative importance of features. The DQN which they used, so the algorithm I previously described, had an input layer of size 6, where the first 5 or last 5, it doesn't really matter in this case, were the composition as it currently is. And the 6th entry was which components was supposed to be changed next. They had 2 hidden layers, I think about 500 on the first and 256, I think, on the second, and an output of 155 possible actions, which was based on the composition limit of copper. Yeah, the replay memory size they set to 5,000, and yeah, these are the details. And the really interesting thing was they did 10 iterations of synthesis and characterization, and this meant that they had, so this is the outer loop, and they came up with 40 new compositions, and this took around 4 days per round. So they were in the lab for about 40 to 50 days. Yeah, the results were quite nice though, since from the 5th iteration, outer loop iteration onwards, the agent actually suggested compositions of higher enthalpy than the initial dataset contained, and 9 compositions with high enthalpy were identified. And yeah, to the author's knowledge, and this is really cool, also the highest reported enthalpy alloy in the titanium nickel-based family of alloys was found with minus 39 joules per gram. Right. And after this, they also, of course, wanted to compare if this was a sensible decision. But obviously, the results are good, but with publishing papers, as we all know, you also need a proper comparison. So they compared on known functions, the genetic algorithms, a genetic algorithm, Bayesian global optimization, and also they looked at DDPG and compared this to the DQN results. And what they found was that reinforcement learning outperformed genetic algorithms as well as the Bayesian optimization for large amounts of iterations. However, for low iterations, reinforcement learning was actually outperformed. And yeah, the main takeaways here were that reinforcement learning is highly applicable when there is a large set space and limited training samples using the setup with the surrogate models. And Also, they mentioned that in the future-oriented self-driven labs, which is really cool, basically the synthesis could be done automatically in a way, and you would basically have the reinforcement learning agent propose new options and automatically do the actual experiments, feed that back in surrogate model, and reiterate basically. And this can then be done automatically. And yeah, this already leads us to the conclusions or takeaways from this short presentation. And it's essentially that, surprisingly, reinforcement learning is rarely used in material science compared to the classical machine learning approaches. However, it offers quite a lot of flexibility in design of both the action space, environment, and also the optimization goals, also with the multi-objective optimizations. And yeah, promising applications, as we've shown, are, for example, exploring the potential energy surfaces, which also in previous lectures, previous talks today have been shown to be a difficult problem to solve. And it's applicable to large set spaces. And the literature suggests that classical approaches are even outperformed when given sufficient training iterations. So yeah. And yeah, it can be coupled with surrogate models when, for example, the labeled training data is sparse. And the example we found was with a Gaussian process regressor for cheap rewards. And lastly, we would also like to mention that reinforcement learning offers a sequential and cumulative optimization procedure. And yeah, it's a great trade-off, or it's easy to balance the trade-off between exploration and exploitation by essentially having the epsilon greedy, at least in the DQN results, and you can vary that however you want to fit your solution. Yeah, and this is also where I'll lead into the last point, which is that it's suitable for path optimization in material structure space. So it can really find or move through the path, which was also previously shown with the transition, what's it called? Transition states, sorry. Yeah, and that's pretty cool. And that's something that, for example, in Bayesian optimization, that wouldn't happen in that sense because it would search essentially where the uncertainty is large instead of actually moving through that space. Yeah, thanks for listening.
Thank you very much, Jean, for introducing us to the interesting field of reinforcement learning. We are very much in time, so I guess we have time for one or two short questions from the audience. Please. Andreas, yes, please go ahead. Unmute yourself. Shoot.
Thank you. Sean, it was a very, very interesting talk. Thank you also for the literature selection because it has very good overlap to what I'm at the moment interested in. I was wondering about one thing you said about the rewards on the Müller-Braun surface. The second reward, what would be your way of how do you explain this reward that the proximity to a known minimum plays a role for the next step?
Yeah, the thing is, I think it was mentioned that it was because of the I think saddle points. So that basically when your reward is sort of when you're moving not towards one of those minima, but you're in between, sort of where it's I think as far as I can remember, it's that you can shift it then sort of in that direction. So because it's not improving, but you want to actually get to the global, it would be sort of like when you get stuck in a neural network that you shift out. But that's at least how I understood it.
Okay. Yeah. Okay. I have to think about it. Thank you.
Okay. But yeah, I've cited all the papers, so I can also get back to you on this.
Yeah, I'll have a look. But if I have a question, maybe I'll get in contact. Thank you.
Okay. Cool.
Any other question?
I may have a question, but I'm very sorry in advance because I know so few on machine learning and on modeling in general. I am wondering what is the weight of the selection of the descriptor to make your reward function. How heavy is it, or how heavy is it on the final results? Because sometimes it's not easy to know exactly which descriptor would be the best for defining and for finding the best material. Because I think that the iterative and the addition of the implementation of formulations is really interesting in our use case, in the project use case. And of course, we would like to come with something, but I think it's not that simple and straightforward to make a proper descriptor and to build the reward function.
Yeah. Okay. So descriptors are, maybe let me ask, are those the features? Yeah. Okay. Sorry. Yeah. So yeah, the features they chose, is that the question? Which features they chose in the paper? Yeah. They did this basically. Maybe they had that on one of these slides. Let me just open it. So they did this with basically looking at the uncertainty of the features. Let me just reshare. I'm no longer sharing, am I? Because I shared the window instead of the screen. Give me a second. So right here. Can you see my screen now? Okay, yeah, perfect. So yeah, they chose. I could look up real quick which features they chose. Since I'm not from the material science field, for me the main focus was basically how they did the feature selection. So from a I would say data-centric view, which was using gradients boosting for the relative importance, the removal of highly correlated features, as well as the features of lowest uncertainty. However, if you want to know exactly which features, I would have to actually look at the paper because, yeah. But maybe I can ask my colleague, Franz. He's already unmuting because he's the physicist.
Yeah, maybe I can jump in. Yeah. So regarding your question with the descriptor, so it's per se not directly connected to the reward function, but rather to the surrogate model you use. Because when using the surrogate model, you feed in the descriptors to represent the potential energy surface. And with the reinforcement learning agent environment, it's that you actually treat the entire surrogate model as a black box. So you do not really care about the descriptors when only considering the reinforcement learning agent, but rather the surrogate model. And of course, this has still an impact. And I mean, based on this paper, they used what is usually done in perovskite structure search, like weighted atomic positions, weighted atomic radii, and so forth. So this is really only the descriptors used in the surrogate model, but not really directly treated by the reinforcement learning agent and environment.
Okay, thank you very much, both of you.
Thank you very much for your questions. I think this brings us now to the last but not least presentation of today, which is given by Robert Behatz. He received his PhD degree from Graz University of Technology, where he was working on probabilistic graphical models and probabilistic circuits. He was then a postdoc at the Medical University of Graz, at the University of Cambridge, and he was also a Marie Curie individual fellow at the University of Cambridge. And now, after being an assistant professor at Eindhoven University, he is an assistant professor at Technical University of Graz again. And I'm very happy that he agreed to present his work on material science to this audience. Robert, good to have you, and please take it away.
Yeah, thanks for the introduction. So I'll just share my screen, I guess. So start broadcast. Yeah. What Bernhard didn't mention is that we did our PhD together. So we know each other since quite a while. So, so okay. Yeah, so I'm relatively, do you see my screen? Do you see my screen? Okay, cool. Very new to material science. So I kind of Yeah, so I'm a machine learning person, probabilistic machine learning mainly. So putting probability at the center of attention, learning machines. And yeah, so like I'm new to this field, but like I want to, and this is like actually rather new work. So I want to talk about this project called Vanilla Flow, which has been funded by the European Union, by the European Innovation Council, about Bayesian optimization for designing electrolyte to redox flow batteries. Okay, so I want to talk a little bit about the motivation of this project, and then yeah, so like the general setup, because like I guess like that's a pretty interesting part. So well, you know, we have climate change, right? So like temperature is rising, the weather is also crazy, right? So like currently here in Styria and in Austria. And yeah, so we want to move towards renewable energy sources, right? So like but they come with their own set of difficulties, right? So like renewable energies are usually volatile, right? So like and intermittent. Sun is not always shining. We cannot really control how much sun we get every day. Like wind is going or not, right? So like, so we either have like a high time of energy or like a low time. So what we really want to do is like when there is currently a high in renewable energies, we want to store that. Yeah, and like if we have like a low in renewable energies, we want like retrieved it from the storage. Yeah. So also we have like now a lot of producers, right? So like photovoltaics and like wind farms, like a pretty scattered producer market. And like really storing energy becomes really key if we want to move forward with this renewable energy. Yeah? So common technologies is like, well, using maybe power, so like water, water pumping systems, right? You would pump up, you would use the excess energy to pump up water into heights, and then you can like release the water and therefore like energy, or like also like pressure air, or like maybe storing it as heat. But one particular, so it's pretty unlikely that that we will have like one way to store energy, but one particular candidate to store energy is redox flow batteries. So generally in batteries, we have like typically two substances, a reduced one and an oxidized one. So like the reduced one really likes to donate electrons, right? So like, so you would have like a reduced species, which would like to donate electrons, like flowing here, and here would have like an oxidized species, which really likes to take electrons, and you would like have like a current, right, electricity. And so in the redox flow batteries, these substances are like in solution. So like you have liquids, and essentially like you have like these tanks, right, with these two species. They get pumped through a cell. In the cell, you have like a membrane which separates the two substances. So also like hydrogen cores, hydrogen nuclei can like diffuse through this membrane, so like that you have like in total a chemical reaction. And part of the chemical reaction is like exchange of electrons, which flow over the wire, and you have electricity. So redox flow batteries are pretty nice because you can design, in principle, the power and the storage independently. So essentially, more storage just means that these tanks become larger, right? You can just need to store more substance, and power can become larger by just having more of these cells, yeah? And by essentially packing a lot of them and putting them in series or in parallel, you can also scale them to the multi-watt regime, which is relevant for renewable energies. They have like no or very little self-discharge, because like what you need to do is like essentially like pump this liquid, right? So like in circles. If you just stop the pump, then essentially like then you don't have like any discharge. If you're clever, you can also design them like very long lasting, so like maybe up to 20 years or so. And also like they can provide electricity for quite some while. So they are a promising architecture to store energy for renewable energy systems in particular. But some downsides is like, well, their energy density is not so high, or like essentially like why the redox flow batteries, which are in use, they are mainly based nowadays on vanadium, which is a little bit problematic. So like, well, you need to mine it, right? So it's relatively expensive, and it's relatively restricted. So like, especially the main producers of vanadium nowadays are China and Russia. And well, the European Union is perhaps not too happy to rely also, right, so to heavily rely on these countries, so which is like part of the reason why this project is interesting for the European Union. Also, vanadium is like, well, at least in the processing, it's toxic. Yes, like it's like not a very clean process. Also, like if you use vanadium, they're usually used with fluorinated membranes. Yes, like another layer of problems. Yeah. So the main idea here is like to make something like sustainable green batteries. Like if you maybe exaggerate a bit, but essentially like developing this thing, so like the vanilla battery. So what is this? So like 2014, a group from Harvard essentially discovered, well, you can actually use organic reactants, so like organic substances in these flow batteries, in particular ketones, which are, well, the key features really like they are derived from aromatic substances. So with the like key features that you have like this carbon cycle here. And so like they had a proof of concept that you can use actually organic materials as catalysts. And so a few years ago, Stefan Spirk and his team, so like from TU Graz and his company electrolyte, they showed that you can use vanillin, yeah, essentially really what is used from, or what you can gain from this vanilla flower, right? So like a pretty expensive spice. Vanillin looks like this, that you can actually transform it into a pair of redox active materials, namely methoxyhydroquinone and methoxyquinone. So like this should be the reduced versions, like you can in the oxidation it would like donate electrons, and this should be the oxidized version and like accept electrons. So like it's essentially by a relatively simple change of this vanillin molecules, you would get like this pair, which you can really use in redox flow batteries. And in their publication, they showed, well, over many charge-discharge cycles, that essentially you can actually build flow batteries with these vanillin-based substances, and would have like, so like that they are quite stable, and essentially that you can like run flow batteries in a long term with them. Another advantage is like, right, so like vanillin is actually a pretty expensive thing if you get it from the vanilla flower, but in principle vanillin can be produced from lignin, and lignin is essentially like a waste product from the wood and forest industry. So lignin is really just like a very complex biopolymer. By chopping it up, essentially you get like a relatively high yield in these kind of ketones. Yeah. So this is like part of this project. So essentially that the idea is like, well, we could scale up this vanillin production from lignin, or like the ketone production from lignin. So currently these waste products are typically burned, yes, like because like they are pretty useless. So, but the idea is we could actually use that to produce lignin, and as a follow-up, actually like substances for these redox flow batteries. So this idea of this vanilla flow project is really to improve this technology readiness level of these vanillin-based flow batteries, because while they have shown, well, this actually works, and actually you can build a decent battery which also would last for 20 years with these substances, the energy density and like the voltage is still too low to really make it practical. So the main purpose of this vanilla flow project, well, funded by the ESC generously, is to really make this more practical and improve the technological readiness level. Oh, TRL, not TLR, sorry. And essentially the main thing is here like that we need to decide that we need to improve our design choices. So there are a lot of different parameters in this battery. So for example, we have felts, right? So like the felts are essentially like in German Filze. So like essentially like here, the porous material, which is connected to the electrode. So essentially that you get like a big area here where the liquid flows through, that you have like a big area with the electrode. So like we need to design a proper felt, a good material for the felt. Also the membrane, which separates the two electrolytes. The whole geometry of the batteries, like the whole layout, is like something you can think of. And in particular, these redox active molecules. So like they found like these two molecules, but like, well, key thing is like that the voltage you get out of these is still too low to really make this practical. So like roughly there's like half a volt missing at least. And like, so the idea is like, let's modify these molecules. Let's find, let's use these kinones, kinone molecules as starting points, but like come up with, better molecules. Yeah. And the main idea is like, let's use AI and like in particular Bayesian optimization to help making these design choices. In this talk I will focus on finding better organic compounds. Yeah, so like essentially like improving these molecules here. So the basic idea is really to mimic kind of what you also would do as a chemist in the lab. So we kind of are doing simulating a chemist in the matrix, you know, like Keanu Reeves, the matrix. So we are experimenting essentially like in silico, so to speak. So the main idea is like we start from a core molecule. In our case, it would be this one, yeah. So like the reduced version of our kinone, and we would so essentially this molecule here has like has some C atoms here, and here. And the idea is like, let's add stuff here, right? So like essentially other molecules, functional groups, in order to modify this. The idea is pretty simple. Start from this core molecule and expand it with these chemical building blocks, or like actually, well, functional groups. So by essentially random choices. So pick a random point, add a functional group. Maybe this functional group has another growing point. So essentially we would like grow this core molecule into a bigger molecule and hopefully change its properties. So the main idea is really just like doing this randomly. So we would have like really a random generator and producing a big library of like modifications of our molecule. So and then right, so like in the real lab, so like a chemist would do something similar, right? So like, oh, I already have a molecule and I modify it in order to hopefully improve the properties. And while the basic notion here is that we produce like now random modifications, and I guess like a true chemist would be a bit more clever. So the cleverness comes a bit later in the context of Bayesian optimization, which I will explain in a bit. But the main idea is really like when we have like this modified candidates, right, all these molecules, that we try them in the lab, so to speak, in a virtual lab. The virtual lab here is essentially called density functional theory. So density functional theory is like a quantum chemistry simulation method, which is like so-called ab initio simulation technique, which allows you to predict certain energy states or like configurations and energy states of a molecule and like make pretty accurate chemical predictions. So the idea, so we start from our core molecule, this MQ molecule, and iteratively just extend it with various functional groups. So if things become too crazy, we just stop, right? So like essentially this molecule can grow, but if it exceeds a certain complexity measured in terms of number of non-hydrogen atoms, we just stop, yeah. This produces a lot of random molecule, and then we essentially just exclude nonsensical molecules by applying chemical heuristics. For example, so in our first chart, we just generated a lot of molecules, and we printed them like 1,000 molecules and sat together with our chemists. And they said, well, it's really weird. We shouldn't have like more than one halogen in one molecule. So like you should also not have a bond between two O's because that's very unstable, and so on. So we essentially, they just sorted out, oh, this is a weird molecule, so like this, I don't like this, and then essentially they formulated these rules, and by applying these rules, we just sort out like nonsensical molecules. But still, after these rules, we can generate a relatively big library of molecule candidates, more than 500,000, so we don't know yet precisely. Here are some candidates. Probably they still look a bit crazy. So like I'd say like out of this 500,000, probably maybe 1% or even less is like really will finally be really hot candidate maybe to try really the lab. So maybe 1% or maybe 1 promille even, yeah. But the point is like we are really creative here. We built really a big random library of candidate molecules and then essentially try them in this virtual lab, yeah. So what we really have is, right, so like this big random library of molecules, and we want to evaluate them. And like there are several things we want from our molecule. So certain key performance indices, KPIs. And the most important currently is like really we need to go up with this open battery voltage. Yeah. So I said like roughly half a volt or maybe 0.7 volts are still missing. If we get there, then essentially like the whole design can really change drastically and maybe can be pushed close to the market. Yeah. So, but also like these molecules need to be soluble, right? Otherwise we cannot build a flow battery with it. We should actually be able to make them, so synthesize them. They should also not be toxic. Yeah. So in particular, so we are currently from our molecules, we are using some machine learning models to predict solubility and synthesizability. They work relatively decent. It's a different story to predict toxicity. So like this is pretty tough to do with machine learning. So this is currently not so on the radar. But the most important thing is anyway this open battery voltage, and so this can be nicely evaluated using this DFT, this density functional theory. So so this open battery voltage can be well predicted by the so-called redox potential. So the redox potential is the tendency of a molecule to receive or donate electrons. So we are working with the reduced species, which has already a negative redox potential. We want to essentially like minimize this redox potential for this species. And the thing is, if you give me one molecule, then essentially I can relatively accurately predict this redox potential with this density functional theory. So the density functional theory is this, well, essentially what it's doing is like a physical model, a mixed physical model, just like, about the energy of a molecule, right? So like it has essentially two parts, the nuclei, which are treated kind of as classical mechanical particles, and the electrons, which are treated as quantum mechanical particles. The main gist in DFT is like, essentially you should treat the electrons as by solving the Schrödinger equation. And the main trick about DFT is that there's a celebrated theorem which allows you to replace the solution of the Schrödinger equation by just like with a summary of the electrons with the electron densities. Like there is a functional which relates to energy, which you would get from the Schrödinger equation by essentially a different functional, which is not exactly known, but it exists, and essentially allows you to compute the energy of any particular configuration of your molecule. Given a geometry of the nuclei, you can essentially like compute the energy state of this atom, of this molecule. So this allows you to compute energies. This also allows you to find like a so-called ground state geometry, also the ground state energy and the geometry in the ground state of your molecule. And so the ground state essentially is like the energy state at very low temperatures, while but with a little bit more effort, you can also get like the so-called Gibbs free energy, which essentially tells you like the energy at the room temperature. And this energy can be relatively directly translated into this redox potential. So long story short, if you give me a molecule, then I can relatively accurately predict the redox potential. So the downside is now the following. So like essentially the picture is like this. We produce now a very crazily large library of molecules, and essentially what you could do is just I go through all these molecules, I compute with the DFT this redox potential, hence the open battery voltage, and then I just take the best. The downside is this DFT is a computational very expensive routine. So like for one molecule, you need maybe a few minutes or maybe even a few hours to compute this redox potential. And with 500,000 molecules, it would take like several years of compute time. So like we have maybe a few hundred CPUs available here at the Institute, and if they would run for a few years, then we could do this. This is a little bit too slow. So what we are going to do here is like being more clever, and this is essentially why I call this the chemist in the lab, right? So what the chemist in the lab is doing is, I have a molecule, I want to modify the molecule to get essentially like a better redox potential, and the chemist in the lab essentially uses like this intuition, right? And this has like prior knowledge, but also uses the experiments they get from the experience they get from their experimentations. they get like kind of a feeling how redox potential is connected with molecules. So they will have like actually a more clever search, right? So partially based on intuition. And what Bayesian optimization is essentially doing is like the same thing, but like with probabilistic reasoning. So in a nutshell, if Bayesian optimization was always working magically, then essentially would like already solve about half or like more or less all engineering problems, because like many engineering problems are of that form that you have, oh, I have a particular set of parameters, a particular set of configurations, and I want to find the best configuration. Yeah. So really what this means is there is like a space of configurations, in our case, molecules, and a certain target quantity, in our case, redox potential. This means there exists a function, right, from candidates, solution candidates to this KPI. And really what you want to do is like optimize this function. So what is now Bayesian about this kind of optimization? The point is that you don't know this function, right? Don't know, this means you don't know an analytic solution which you can, or like an easily accessible solution translating candidates into your target quantity. Yeah. So the only thing here is like what you can often do is like evaluate it pointwise. Yeah. Given a candidate, with some effort, you find this KPI, yeah? Either in simulation, as in our case, or by doing maybe real experimentation. Yeah. So roughly what this means is like you have like this input configurations, or parameter configurations, and the thing you want to optimize, and this function is not known. So what is the Bayesian reflex? So I call this the Bayesian reflex. Whenever something is not known, I put a prior on it. Yeah. So essentially that's Bayesianism in a nutshell. Whenever you don't know something, you put a prior on it and perform probabilistic inference with it. Yeah. So what you do is like, oh, there exists a connection between molecules and redox potential, and I don't know this function. So I put a prior on it and like a distribution over functions. And what I do is whenever I observe data, I condition my current belief over functions to get a posterior. Yeah. So by Bayes' rule, and therefore this is called Bayesian optimization. So I start with a very vague prior, so it could be any function relating molecules with redox potential. And as soon as I observe data, meaning, oh, I've observed like the redox potential for a few molecules, this gives me some information how this function actually looks like. So here in this cartoon, there's like illustrated here, it would be a solution space, and like your uncertainty, right? So your distribution here is like typically illustrated with this uncertainty about what this function really means. And the strategy of Bayesian optimization is now combine two things, namely exploration and exploitation. Exploitation means I want to try solution candidates where my uncertainty is high, maybe here, or also here, or also here. And exploitation means I want to try candidates which are likely close to the optimal. Yeah, so like you combine this likeliness of having a maximum together with the uncertainty in the so-called acquisition function, and you maximize the acquisition function to provide the next candidate. I don't really know what the acquisition function here really is doing, but like it's kind of combining the idea where could be a maximum together with, oh, there's some significant uncertainty here. So if I sample here, if I get like the value here, I learn more about the function and are probably also close to a maximum. Yeah. So really, Bayesian optimization is really the same thing as you would do in the lab, right? So like sometimes you do experiments to learn more about the process. Sometimes you do experiments to get like a really good solution. Yeah. And the main gist here is Bayesian optimization is doing that, but like just rigorously with probabilistic inference over the set of candidate functions. Yeah. So we are doing this here. So like, and here are some preliminary results. So like I said, in total, we would have like 500,000 molecules. So far, we take a subset of 40K molecules. And right, so like we have like this nice DFT, which would compute our redox potential. We are replacing this now with a way cheaper approximation, just taking a cheaper basis set of the DFT and computing the ground state instead of the Gibbs free energy, which is like a factor 10 to 100 times faster. We do this for the 40K. We do this in order to have a ground truth. So here we can actually get the exact maximum. And we just demonstrate that Bayesian optimization here will help in the following. So like here we have two versions of Bayesian optimization. This is using a Gaussian process. This is using some Bayesian neural network. But in either case, here we have like iteration of Bayesian optimization, right? So like in each iteration, Bayesian optimization provides a new candidate. Yeah, so like try this candidate, then try this candidate. And whenever, it's like we do this over 10 runs. And whenever we found in one of these runs the exact candidate, then we get like essentially like an increase here. So like this is roughly the probability, how fast will Bayesian optimization find the true optimum. And while it's, so we cut off at 1,000, but roughly we get like about 80% chance that we find the exact maximum with among 40,000 molecules within the first 1,000 trials, which means you just need to scan for 1,000 molecules, right? So like quite likely to get the maximum rather than through 40,000 molecules, which is like times 40 speed up. Yeah. So this essentially just like a proof, right? So how did we do? So here we use the GP. Here we do a Bayesian neural network. So of course this. So how did we represent the molecules? Essentially, we just derived certain chemical features with a computational chemistry toolkit called RDKit. So just derived a bunch of chemical features, took the principal component analysis of that, and essentially like that was the feature space provided to these Bayesian optimization routines. But the main thing is like proof of concept, like in small this works. In future work, we want to scale this up to our full library, use an actually accurate redox potential estimates using the more accurate versions of DFT. It will also be interesting to compare these different levels of approximation of DFT. And at some point when we have like really find good candidates, then we really want to try them in the lab, which will be done by our colleagues. Yeah, so this just like this ongoing work has started like about half a year or like a little bit more than half a year ago. And at this point, I want to thank the whole team, also the Vanilla Flow team, and yeah, happy to take any questions if there are any. Thanks.
Thank you very much, Robert, for this nice presentation. It was very interesting to see this, see more details about Bayesian optimization, how it actually works. I much appreciated it. Before we start with the panel discussion, I think there is time for 1 or 2 questions, if there are any from the audience. Maybe I have one. Oh, yeah, and Andreas also has one. That's very good. Andreas, maybe you start, please. Go ahead.
Thank you. I was just wondering about the workflow that you showed. When you said you changed the moieties, or you changed the chemical setup of the molecule, and then you do a DFT approach. Is it really this way that you are modifying a chemical group and then you start right away with DFT, or is there anything in between? Because this might be very far off the minimum energy geometry, and so I was just curious about having a force field step in between or something. I would assume as a meaningful approach.
Okay, so like not entirely sure. Hi, Andreas, by the way.
Hi. Yeah.
Not entirely sure whether I understood the question. Like the workflow is like really first, okay, just like go crazy and start this huge library. Yeah, the library is represent like just 500,000, 700,000 molecules, which are really just like, well, randomly growing this core molecule. And we are representing them in so-called smiles strings. They are, well, essentially like computer-readable chemical formulas.
Yes, I see.
The DFT is then doing, right, so when we do DFT, is like we first find an initial geometry using RDKit. Giacomo, my PhD student, could tell you more, but essentially like this seems to be kind of a state-of-the-art initialization method for the geometry. Then you run DFT, right? DFT gives you like the forces and like you do like the geometry optimization. Yeah.
Yes. No, Robert, you already answered my question. So I would have suggested smiles, but it is clear that you're using it. There is no geometry optimization needed because it is basically obvious from how the smiles file. So it's not coded in the smiles file.
Right, yeah.
but it's easily generated from there as a good guess for DFT. So everything answered. Thank you very much.
Up to here, it's like just smile strings, just chemical
Okay.
formulas, and then we,
do the
okay,
DFT.
Thanks.
Okay, thank you very much. Thank you.
Thank you.
Maybe one follow-up question. I was found it extremely interesting that you compare Bayesian neural networks with Gaussian processes. And in your opinion, what would be the pros and cons of the two methods? Is that there's something that you can say to that? I mean, like performance-wise, they look quite similar, but yeah. What would you say?
Well, GPs are nicer analytically, right? But I guess like it's Bayesian neural networks use this secret deep learning source. I guess like deep learning and like sometimes just like having like this edge over simpler methods for some not well understood reasons. So like Bayesian neural networks seem to work a bit better here. I guess like that comes from flexibility. So at least in principle, in GPs you would have like closed form inference, a little bit expensive and cubic and whatnot, but principle closed form. While in Bayesian neural networks, of course, you need to worry about the inference, right? So like how to perform actually the posterior inference. So this is kind of relatively easy, right? So like O of N3, right? While here it's like, you need to approximate and hack, right? So, but apparently, if you do it clever, it's like I'm not entirely sure what kind of I guess like some latest Bayesian optimization technique on not sure, some paper. If you do this well, then I guess like Bayesian neural networks can have an edge here. Yeah. So also I guess like the neural networks, right? So like you can play with structural assumptions, can have like I mean, you can use like graph neural networks, but I guess like you can also like use like a graph representation here. Yeah. So maybe Bayesian neural networks are just like a little bit more flexible in terms of architectural choices. Yeah. But ultimately,
Thank you very much.
That's my hand-waving answer.
Excellent. Thank you very much, Robert. I see Franz is raising his hand. Franz, please also shoot your question.
Yeah. Okay. Thank you very much first for a very interesting talk. My question goes in the direction, since in the beginning you mentioned that you actually have several targets you want to optimize. So my question would be, do you think or how you would approach this? Would you consider then constrained Bayesian optimization, or actually do on all of these, like each fit a Gaussian process and do this? So what do you think would be the best approach for this?
Yeah, so good question. Yeah, so it's interesting. So toxicity is definitely hard from a machine learning perspective, and like there is actually a project partner testing for toxicity. They're in Spain. Yeah, they're doing this with zebrafish. For solubility and synthesizability, it's a bit, would we have a constraint? Would we exclude candidates if they are not soluble enough, if they are not synthesizable enough? That's actually an important question. So I'm not sure, right? So if we exclude them from the search space, this could hurt exploration, right? So sometimes, so you could actually not entirely sure. So or you could, not entirely sure. You could, for example, right, so you could have like a combined KPI or like a combined target function by having so I prefer redox potential 5 and solubility 2 and synthesizability 1, right? That would be one. Constraint optimization, so these approaches exist for Bayesian optimization. I guess they're finicky, and it's also, you could also they are relatively easy to, there are machine learning approaches where to compute these, so you could exclude them a priori, but I'm not so sure whether this is a clever move, right? So if you have actually a big search space, and now you kill lots of it by, well, that's not soluble enough, not synthesizable enough, that actually Bayesian optimization will learn less about the redox potential. So sometimes it might be beneficial to know the redox potential of a not very soluble, not very synthesizable candidate. Yeah. So yeah, not entirely sure yet. Yeah.
Very interesting.
Okay, thanks for the answer.
But I think that is a very nice segue into the roundtable discussion, where we can continue along exactly these lines, trying to find pros and cons of the individual approaches that were proposed and that were introduced today, and maybe also discussing how this could be connected to Knowskite X or how this could be applied for perovskite data. So maybe as an icebreaker, I would have a question for all the speakers. We have seen probabilistic graphical models where some relationships were based on known physics. We have seen physical models like the embedded atom model that are augmented with neural networks. And we have seen, I think, well, please correct me if I'm wrong, purely probabilistic, purely data-driven models for Bayesian optimization and reinforcement learning with you, Sean and Robert. So is there some common ground that can be covered? So do you think it is possible to include the, I don't know, the embedded atom model that Andreas was talking about in some reinforcement learning setup? Or do you think that Gaussian process or Bayesian neural networks can be constrained with physical prior knowledge? Are you aware of some literature in that direction? This is mainly a question to the presenters from today.
So yeah, so I mean, physical knowledge embedded in neural networks is doable, also in Gaussian processes, right? So like so Sasha Ranftel is working on something along these lines, right? So.
Yes, as far as I understood, the Gaussian processes in your case are surrogate models that are trained on DFT outputs, but they are not constrained to be physically consistent. Is that right?
No, yeah. So like the search space, or like the input space is right. So like chemical features from RD kits followed by PCA, right? And that's it essentially. And then like yeah, some Gaussian kernel, probably a Markov kernel, right? So like no physical knowledge yet there, yeah. So would be interesting, yeah. Finicky, right? So like how do we incorporate physical chemical knowledge in such models is an interesting thing, right? So
maybe can comment from my point of view. So in our active learning loop, so in terms of resources, the main bottleneck is actually synthesis or the characterization of new data points, right? That means if we have physical models which are so predictive that they can replace experiment and are still cheaper than experiment, then this is attractive for us to make use of them in our modeling chain. And along that line, like embedded atom models could potentially improve the situation if they are well parameterized for our use cases. I think how good I'm not. Of course, this parameterization itself can be still quite costly if you have, for example, multi-component alloys or steel. So then you have magnetism coming into play. But once you have such models, they can be really useful also and included in the modeling chain. Well, actually, in the modeling chain, in the experimental prediction of new data, experimental classification, characterization of new data points, right? Like this, yeah.
Thank you.
So since you already mentioned the connection to reinforcement learning, I recall what Jean was presenting. Like indeed, you can, like always in this setting where you have this reinforcement learning agent interacting with the surrogate model, always exchange this surrogate model with a like more physical inspired model. And actually, I think this is the way how it should go, that we actually use more of the physical knowledge we know from like the ab initio calculations, the simulations, to build them into the models to make them physical, more consistent, and use them then in certain settings. So, yeah.
Okay, thank you very much.
We also have to comment was from the materials at this point of view. One major problem is that if you predict a suitable material with DFT or like good at music modeling approaches, is that it's mostly still an ideal material, and what you produce in lab is limited or often also quite heavily influenced by the experimental boundary conditions, also by processing, which is very hard to model, like processing temperatures, which then like impurities, like the microstructure that forms. I mean, it depends on what exact materials exactly you look at, but many technologically relevant materials are not ideal phase pure perfect materials, but they produced some kind of a lab and using some kind of processes where a lot of boundary conditions come into play, which cannot be represented and for a long time still will not be representable by ab initio approaches or atomistic modeling approaches.
Thank you very much. Maybe a related question that is, I'm also not a physicist, so I don't, probably it's a stupid question, probably it's obvious. We have seen the potential energy surface that was motivated from the perspective of structures, so like structure property relationships. But then we have seen also composition property relationships, if I remember correctly, and then also mixtures of those. So I think, Andreas, you had these different compositions, but you also your clusters had different sizes. Are these three types of potential energy surfaces so fundamentally different that you need entirely different machine learning methods for representing them and for optimizing or for finding optima, or are they sufficiently related that that technique from model A can be reused for model for potential energy surface A can be reduced for potential energy surface B?
Yeah, so the concept of the potential energy surface is really the energy as a function of these internal degrees of freedom that are related to moving one of the nuclei, right? But then you also have degrees of freedom that are not like more abstract, as you say, if you want to change the ratio of certain compositions, or if you go from one size to the other, and you would use the same computational technique for them. I think this is also essential if you compare between them, because otherwise you introduce another large bias. If people, I mean, there's so much computational chemistry data already on the market on some systems, but it's very hard to compare, even though they are almost exactly the same, just a different basis that has been used or a different function has been used. And then you don't know how they are actually related, how to compare them. So it's not very, it's a problem to use mixed data from different methodologies. So it would be great to have everything produced in one go. But this is very often not the case, and so you have to find a compromise. And so people are working on unifying these databases that they have created and to actually translate. So people are learning how to, for example, map from one functional to the other without performing the actual calculation, or how to extend to a basis set limit, for example, or try to make it more interchangeable. Like, yeah.
Very interesting question. I would have had a very close or related question. Maybe I ask anyway, and maybe also address Professor Hauser on this regard. So I know from crystal structure prediction that you basically have two approaches how you would model your target quantity, and you spoke about the Barenello approach, where you actually model the target quantity as a sum of atomic energy levels. So this, of course, I mean, with this you can really produce very accurate predictions on, like, when you really want to have, let's say, phononic calculations, and you really want to resolve any displacement of atoms when modeling the target quantity. But this comes at the cost that when you really want to look at large structures, that maybe you need a lot of training data and just your search space or your composition space is too large. While there's the second approach where you, as Bernard mentioned, that you really have the structure-based approach of describing your material, your crystal structure. So my question would be, what do you think is like the more suitable approach, or like what are the benefits of using this very atomic-based approach versus the structure-based approach?
Yeah, it's a good question. I think in this case here, if I compare what we're doing on the clusters to, for example, what Robert was showing, Robert is indirectly already introducing physical knowledge when he converts somewhere from the SMILES structure data to the geometry that he uses then later on the DFT. So there is one step in the pipeline that does a standard translation of this moiety that has been attached or has been changed in the molecule to a meaningful geometry before the DFT code is starting, because otherwise it would lead to nowhere typically. If you just make a by hand replacement, this is far off any equilibrium, and often so far off that the DFT code would be able to find the local minimum in this area, or a wrong local minimum eventually. So this is already in there, and so I think it's somewhere in between. If you have physical knowledge at hand, if it's somehow easily integrated, then this makes perfect sense. But in our case, we have simply so many isomers from how you mix these two metals, for example, and the Barenello is exploding here in terms of effort. If you have, say, more than two, if you have 3 or 4 different metal components, because then this goes up exponentially in terms of how to rearrange or how to mix these different elements among each other, because this makes it necessary to have many different neural networks to describe this situation of having either an atom of type A surrounded by something, or atom type B surrounded by something, and they will have to be trained basically separately and then built together to form the energy. So it's very it's not scaling in a nice way, I have to say, if you mix it, if you have more elements involved. So
yeah, great insight. Yeah, I also have the feeling that those approaches which are based on this atomic level, they let's say their scalability is less compared to the other approach, and especially when we're dealing with this large compositional spaces, then maybe this approach is not suitable.
Yeah. So it's a wish. It's a big part of the community that is trying to improve methodologies in electronic structure theory, is trying to find some sort of linear scaling in describing certain properties. Because of course, at some point, if you move sufficiently far away, this type of like an atom-atom interaction will no longer play a direct role. So the longest type of interaction you will find in molecular systems would be van der Waals type interactions, and they are also dying off at, say, between 10 and 15 angstrom. This is so far away, it doesn't matter anymore. But in metallic systems, you have this correlation issue with electrons being completely delocalized over the whole bulk structure in principle. And so this is where you have to deal with the different methods, and you cannot assume these correlations to die off. So it makes a difference if you have 1,000 atoms or if you have bulk. You're still not there in the simulation.
Very interesting. I think we're now very engaged in the discussion, but it is still time to come to an end soon. So I will ask once more if there are any questions or comments or requests from the audience. If you look at the chat, if there is something. Fotis, yes, please. I don't know if you can speak. I'm not sure if you can. Excellent. Yes, then please go ahead.
Okay. Hi, my name is Fotis Katsaros, and I'm from Athens, Greece. I'm collaborating with Elise and Know-How Center in a project, and it was very interesting all this session, although it was not my field because I'm mainly experimentalist. So I have a question regarding porous materials. You mentioned that about porous material. In most of the industrial cases, porous materials are used. So how easily is to model this type of porous materials without actually knowing exactly the topography of the nanostructure?
If I may try to answer a bit here, in this case, I would hope that there are certain template structures where you can go beyond a fully atomic picture if you know if you are somewhat constrained to certain types. If you're having metal organic framework structures or something like this, I think it is convenient to switch to a higher level in terms of structural knowledge and try to learn how an energy structure relationship, or how to learn the energy structure relationship on this higher level based on for example, ab initio data for the fragments that you're using when you build it or something. But I guess what is your concern on the long run is not just the structure itself, but also how certain interactions take place in the structure, right? Like gas absorption, so this is more a molecular dynamics issue where you try to find a cheap method that allows you to do dynamics that is as close as possible to the ab initio molecular dynamics, which is simply too costly to perform. And I think this is something where you do a lot of, where you might be successful in training, for example, a force field or a force field plus some machine learning improvement to some DFT data in order to perform your molecular dynamics simulation later on a level that is almost as good as DFT, but at a fraction of the cost. So I think this would probably one way of dealing with this, but it's also taking time because you have to train your model at first to DFT data, for example.
And probably starting with materials with known structure like MOFs, you said, or some SBA systems with cylindrical pores, so you know exactly the geometry. Then you can try to simulate some random materials like activated carbons, etc.
Yes, I think, but if you are on a higher structure level, the replacement of certain linkers by others, when you know what is the physical and the chemical property of this linker, of this linking unit, might allow you to already predict a certain performance of your porous structure with regards to the adsorption of this or some other material, simply because you know the physics for the interaction of your gas molecule with this new linking unit or so. So I think there is a lot that can be learned on a higher level of the structural hierarchy. But it's all building up. At first, you have to know what's happening on the atomic level, just dealing with one specific metal center in this environment or with one specific linking unit. Yeah, so it's a gradual build, I guess, from the atomic structure and then going in the hierarchy slowly up with getting more information for more complicated structures if you're sure that your atomic description is suitable.
Okay, so thank you very much. Thank you.
You're welcome.
Thank you very much for this. Thank you, Andreas, for the answer. I think we will take one final question by Paolo. Please go ahead.
Yes, thank you. Well, first, I would like to thank all the contributors, although I was not that able to follow precisely the details. But I perceive that overall there is an attempt to use to develop some sort of shortcut method to deal with a common issue that is modeling the atomic structure. So at the core of most of your approaches, there is a TFT calculation that is known to be quite costly in terms of computing time. And indeed, my question is, to what extent the different approaches to be more effective or save time or to investigate a larger design space using different approaches is tailored to DFT calculation. And indeed, the question that also Fotis was asking is, how can this approaching can be useful? To my understanding, the question of Fotis was the possibility of by using these approaches to design porous material that probably is not at the atomic level, but is at a higher level of texture of the material. And in my interest, that could be to what extent these approaches to investigate many different cases could be used when the core simulation is not a DFT, but perhaps a CFT. So computational fluid dynamics simulation, so something that is not at the atomic level, but at another level, but still the single simulation could be the bottleneck, a cost-intensive step that you cannot multiply by thousands.
Mm-hmm. So
perhaps I misunderstand you. I misunderstood you, but I got the impression that many of the Bayesian approaches are trying to take advantage of some feature at the atomic level of the type of species or reaction that you are investigating. So they are, in a sense, tailored to very specific application that is simulating the reactivity at the atomic level.
Maybe I can comment from the work we are doing that I have presented. In our modeling chain, we have included for the Bayesian optimization different models, like thermodynamic models based on Calfat databases, or also other empirical models. So in that case, we are actually not going to the atomic level, but using modeling approaches on other levels. So and which are useful for us also, really. I don't know if I understood this question correctly, but so in our case, we definitely do not focus on atomistic modeling for the Bayesian optimization.
Okay.
Thank you very much.
If I may add, to this answer, I would say if you can get away without modeling on the atomic side, this is perfect, because it will save you a lot of worries. It's just that in some, so many of us were talking about chemistry, and chemistry means that you're forming and you're breaking bonds, and so there is no way you can get away with a granular picture that is not dealing with atomics, with the atomic structure. But if you are interested in a physical property, such as maybe you are interested in the diffusion of metals, we also investigated what happens to metal particles if you heat them, if they're sitting on a surface and so on. Then you can even try to use like cellular automata or some finite differences methods, and you are solving the problem on a much coarser grain, where you are handling these atoms not separately but in bunch of hundreds, for example, and you have some other physics like Fick's law in for example, where you have different concentration, and this gives you a gradient and tells you how matter flows. Then this is of course the way to go, and no need to go into the atomic structure. But in chemistry, typically you can't really get away with such a picture, because it is at the atomic level that the bonds are formed and broken, and so this is usually not a possibility.
Mm-hmm. Mm-hmm. Thank you very much. It's a very interesting insight. There is one more hand raised, and I think this makes it really hard for me to close the session. So, Parul, please shoot. We can't hear you. Hello?
Hello, can you hear me now?
Yes.
Yeah, so I have a very, I have a question. Like, I want to know what methods can we use to validate and test the performance of our ML model integrated with DFT theory?
Well, you can use experiments for that, right? I mean, DFT is already quite accurate normally.
Just I want to like for the ML models itself, like if you want to test the ML models that are integrated, that are trained with our DFT data, like what method we can use for it?
May I ask, so just to make sure if I understood correctly, you want to validate like the predictive power of your machine learning answer set is trained, for example, on DFT data in comparison to real life, right? So then, of course, as Jürgen said, if you have experimental data, this is what you would hold it against. If you don't have it, then you would go to a better method than DFT. But they are typically very, very costly. And the gold standard in computational chemistry is called coupled cluster calculations, but they are scaling with the fifth order of basis set size. So this is something that is only available for small or medium sized molecules and not applicable to anything larger. But you could probably break down your system into a smaller size and then make a comparison to what the coupled cluster theory would tell you in comparison to DFT, and then you would get something that tells you how close you to the best that theory can do for you at the moment, which might still not be good enough in comparison to the experiment, I have to say, because this is still a certain gap depending on the size of your system and the approximations you have to make in order to be actually able to get out some meaningful result. Yeah.
Thank you so much.
Thank you very much. Thank you very much, Elise, for introducing the project. Thank you, the colleagues at Warrant Hub, for organizing this webinar so well. And thank you for all the speakers for presenting their work and being so timely and sticking to the 30-minute limit. And also, thank you very, very much for participating in this roundtable discussion. It was much more active than we expected. So I seriously hope that we can continue this discussions in the future, maybe in another webinar. Okay. Have a nice afternoon and a good day.